This conference will now be recorded.
Okay, we are actually officially at the top of the hour. As we were mentioning, welcome to the Heat Reuse group. We expect actually quite a large group of people that will join us in a few minutes. There was a call, a very popular call immediately before us, so they were running a little behind. So we're gonna waste your time for a couple of minutes now chatting about the weather, and I would say around 8:02, 8:03, probably we will start with the introduction of our group, and Jaime will talk about that. This is, of course, the heat reuse call. We alternate this time slot. 1 week is heat reuse, the other week is advanced cooling facilities. Which is equally interesting is the integration of any kind of cooling solution into the facility, the building. So that it's actually very, very interesting. But our heat reuse is more interesting. In case you have to choose. Okay, I would say another minute or so, and then we can start with the introduction, and Jaime will take care of that.
Yeah.
And then at around probably 8:10, 8:07, 8:10, we will let Seth talk about their experience about recapturing the heat with CO2 as a refrigerant, which is actually a very brilliant idea. Do we want to start with the introduction of our group, maybe, Jaime?
Yeah, let's do it. Great. So welcome, everybody. I'm not seeing actually if you are all new people actually, or you already have been in our calls. But in case it's the first time, that's why we do this introduction. So welcome to the Heat Reuse workstream. This is an OCP group, Open Compute Project Foundation group. We are actually now, okay, sorry, the slides are moving. I have to change my mouse. Exactly, we have today a guest presentation, Emmanuel Carnot. So Seth will present us how actually to recover data center heat using CO2 as a refrigerant. But first of all, I want to actually talk about our workstream. We have a wiki page, is that one there? Yeah, that one. I think usually Cosimo makes copy paste of this in the chat box, so you can.
Yes. Because of the limitation of this tool, if people join later, they cannot see the past chat.
You're right.
So,
right,
so yeah. I will add the links of our group and our emails and everything at the end of the call. So everybody, right. or in the middle of the call, so we know that we capture everybody.
Perfect. If you click on here, actually you come here. This is our wiki page where we actually have the relevant information. We have the calendar, we have the minutes calls, if we do them, actually, let's be honest. You can click also on the map we are actually developing. This is actually the heat reuse map. You might have seen that already on LinkedIn. We have all the heat reuse use cases we could gathered. And here are all the places or the locations, yeah, where there is a known heat reuse use case. We would love to have that a bit enriched in details and know a bit more of these use cases. Know, for example, how big are those data centers, how much heat is recovered, what is the heat cost actually, what is this being used for, and a bit more. And if there are here some people in this call that are affected by these dots here, I actually ask them, please share more details, and share also the website where you have those details. At the end, it's also can be relevant also for your organization to share that story. We are happy to do that for you guys and fill this map as much as possible. So coming back to where it was, sorry, I don't find the presentation, is that one. So this is our mail address. If you want to write us something, some comments about our calls, if you want to give us the information about your use cases, if you have some suggestions, feel free to write us. Yeah, we are Cosimo Piccioli from Alfa Laval, and I am Jaime Comilla from Talentiv. Why are we doing that? We're doing that actually to highlight the challenges and the opportunities, especially the opportunities of heat reuse in data centers. And actually, at the end, we want to end up with some outcomes. So we are writing a guideline of tricks or things to take care about when some project is getting developed for heat reuse in the data center? What are the key things to take care at the beginning? And what are also for example, a way of monetizing the heat of the data center? We want to put there some examples, some calculations of cost, and some energetical calculations as well. But at the end, what we want is to push for a change in the industry, right? So as I told you, we have written already a couple of things. So we have this is the guideline. We already have a lot of content. We are assuming that in the next weeks, months, this will be quite finished and open for your suggestions. Actually, you have a direct link to this guideline in the wiki page I showed you before. So you can actually click on that and even leave some messages. I think it's open for everybody. If not, let me know.
Yeah.
The other thing we are also doing is, I'm maybe extending this too much, this introduction, but I will be fast, is the Data Centers Heat Reuse 101, which is a shorter version. We want to write a white paper, much shorter, much more to the point. So you guys also, I think we will have this finished in the next weeks. We will open that also to the public. And besides this, if I find it, yeah, we have also all the past guest presentations uploaded. They are all online as well in our wiki page. If you want, guys, you can also see them.
Yeah.
Having said that, I think.
Yeah, I think we are getting people are still joining, but if you let's say basic instructions, if you have questions, the presentation is going to be about half an hour, right, Seth, more or less. Yeah. So we will have time for questions at the end of the presentations. That being said, if you have something that it's really pertinent about what Seth is talking that specific moment and you think that adds value, you can put the question in the chat and we will check the chat. And that being said, I would say without any further ado, Seth, I'll give you the stage.
All right. Well, thank you.
Sorry. One last thing. If you can please mute yourself. If you don't do,
I will mute them if not. Don't worry.
Yeah, if you don't do that, actually, we will mute all of you. You can unmute yourself, but because sometimes there's some background noise that it's a little distracting. Sorry, Seth.
No worries. Hopefully you can see just the presentation.
Yes,
but,
we can.
All right, yes. Good. So thanks to everyone for taking the time to come listen to us. I want to give you an introduction about what M&M Carnot is doing with natural refrigerants, specifically how we're taking heat from data centers and using it in a useful way. But I think what I'd like to talk to you about is I'm going to get right into it and give you one of our latest designs of a chiller that's used in a data center that takes heat and moves it into a building. But then I'm also going to talk about how M&M Carnot got into data center applications. And while we were doing that, on the industrial refrigeration side of our business, what we were doing for heat reuse there. I think when you talk about data center cooling and industrial refrigeration, there's a lot of things that can come together. And I'm just going to give you an introduction of what we're doing and what we're thinking, and also talk a little bit about some of the things that we see in the future for computer room cooling, and where we think we can go from where we're at right now. Just a brief history of M&M Carnot. There was two companies back in 2018 we merged. It was M&M Refrigeration and Carnot Refrigeration. M&M Refrigeration is based in Maryland, down here in the States, and Carnot Refrigeration is up in Trois-Rivières, Quebec, Canada. So both companies were focused in using natural refrigerants in the industrial refrigeration market. So you know, our company was founded with supermarkets, food processing, food storage facilities, and things like ice rinks. But then as of around 2012, we started getting into data center cooling. And I'll talk a little bit about why CO2, natural refrigerant, is a perfect refrigerant for data center cooling. But I figure, let me get right into one of our latest designs for a chiller that does heat reuse. This is a machine it's rated around 280 kW worth of cooling. So the room that it serves has about 6 chilled water crack units that are scattered throughout a small data center in a building that's also has office space. So the idea was that we could, with CO2 refrigerant, we could provide the cooling for those 6 tons or 6 units at 80 tons, and then move that heat into a building hot water loop to provide heating for that building. So that building was heated by natural gas boilers, and I think there was 3 in the building, but we figured out a way to take the 80-ton machine that would handle the load for the data center space and basically provide 300 kW worth of heat that the building could use. So we were eliminating the use of the natural gas boiler, but running a chiller that would move the heat from the data center into the building space. So just a couple of the specifics. It's it was a 44 to 56 chilled water loop. I think in Fahrenheit, but I put the Celsius there as well. So 13.3 and 6.7. I think I reversed that, but you know, so those are the temperatures that the data center needed to cool the equipment at around 160 GPM. But what we were able to do with the refrigeration system was to basically generate 300 kW of usable heat that would go into the building. This was an area of Canada where electricity is much cheaper than it is where I live down here in the States. But they were able to, in nice round numbers, basically save around $70,000 worth of natural gas every year at the expense of about $20,000 worth of electricity. So I'll get in, you know, I showed a couple pictures and I'm missing one that I'm going to show you in a second, but on the left, this is our indoor unit. It's a dual circuited machine, so it has 2 compressors, 2 evaporators, 2 receivers that's connected up to a dual circuit gas cooler, which is the picture on the right. That's on the roof. It's a pretty compact footprint, but this kind of just shows you that we have 2 circuits on this one machine, 40 tons of circuit, and the piping for each circuit's separate. Real quick, this is you know, the piping schematic of this chiller, and it basically, let me hold on a second. Come on.
We can see your pointer set. So
okay, well, so this box right here is that chiller that's located inside of the mechanical space. So you have your compressor down here, which sends the hot gas to these heat exchangers. These heat exchangers are basically what decides if the building needs heat at the moment, and if it doesn't need heat, these valves close and send that hot gas up to a gas cooler that's located on the roof. So in wintertime operation, instead of rejecting the heat to the atmosphere, you're rejecting it into this building's hot water loop. And what we're doing is that hot water loop in that building requires 131 degree water. So this was basically it was a sweet spot for us because we were able to give you a little bit more heating than we could give you cooling with the compressor heater rejection that was added to the CO2 loop. But these heat exchangers up here, I'm showing in the picture here in the middle. So this is the difference that you would see between a normal CO2 based chiller and one that has heat reclaim. These are, it's not as good of a picture as I would have liked to show you, but it was one that I was able to take with my telephone when I was up there a couple of months ago. But these are two heat exchangers, one heat exchanger for each circuit. The CO2 comes in that heat exchanger, and I can reject, like I said, heat into that loop, or I can reject heat out into the roof. So this is the latest design of a small chiller that we have for a building. But I'd like to kind of give you an introduction of how we got into the data center business. Some brief history about CO2 as a refrigerant, I think, is a good place to start. But when you think about industrial refrigeration, the two refrigerants that they used were ammonia and CO2. With the invention of synthetic refrigerants, CO2 started not to be used as much. And basically in 1950, no one was manufacturing equipment that used R744 or CO2 for industrial refrigeration anymore. But then came the Montreal Protocol, and for those who aren't aware, that was back in '89 where we started saying, you know, that these synthetic refrigerants are putting a hole in our ozone layer. We need to do something about it. And once that happened, people started looking into using CO2 as a refrigerant once again. After the Montreal Protocol, one of the things that happened was we still, the Kigali Agreement said, you know, these HFCs are still have very high global warming potential. And, you know, we came up with refrigerants, or everybody came up with refrigerants that weren't putting a hole in the ozone layer, but still had significant global warming potential. And the Kigali Agreement was something that said, okay, well, we need to phase down these refrigerants that still have higher global warming potential. So this is a really great conversation to have, because just recently down here in the States, we ratified the Kigali Agreement within the last couple of months. I think you know, I was reading about it, and the Senate passed it I think in a historic bipartisan fashion. This is something that needs to be considered now if we want to reach our goals for, you know, doing our part to making the world more sustainable than it is today. So that was the you know, where we are as a company specializing in using natural refrigerants, but specifically, our data center cooling equipment uses carbon dioxide. So I put this chart up just to kind of show you guys some of the properties of CO2 compared to some of the other synthetic refrigerants that are out there. This chart is compared to ammonia. Ammonia is another natural refrigerant, but can be fairly toxic. So if you're deploying this in a data center space and you have an ammonia leak, it's that would be a concern, where CO2 isn't toxic like ammonia or the other synthetic refrigerants could be. But one of the things I like on this chart is it shows the capacity of CO2 as a refrigerant. Compared to ammonia, it holds about 86% of the amount of heat that ammonia holds. Compared to the synthetic refrigerants, that's a little bit less. This becomes important because you need less refrigerant to move the same amount of heat that you would need in a synthetic refrigerant-based system. So what had happened was our president, Marc Andre, was out giving presentations of the benefits of CO2 refrigerant for industrial refrigerant applications. And a large telecom provider up in Canada came and said, you know, I have R22 cooling systems for all of my data centers scattered throughout Canada, and they're going to be end of life soon. So I'd like to come up with a solution where I can replace all of this R22 equipment with a natural refrigerant like CO2. So we formed a partnership, and we developed a prototype and a design, and we tested it, and we basically did everything to that machine that we could think of to see it work and to try to get it to fail. But we came up with a design, and shortly after, or a couple of years afterwards, it was deployed in one of the first data center rooms for a telecom provider. So we had one size, one footprint, and then we were asked to build a different size and another size. So now we have a pretty good catalog of computer room cooling units that will allow you to use CO2 and take up a smaller footprint than what you would see in the synthetic refrigerant type system. The nice thing that I'll talk about is the properties of CO2 as a refrigerant. With CO2, it is a high pressure refrigerant. So one of the benefits that we get is when your ambient temperatures outside allow, you can do free cooling. So basically, a data center is a constant source of heat. You run the heat over your evaporator coil, that gas expands and moves up to your gas cooler. When the temperatures outside are cold enough, all of that gas turns into a liquid and falls back down to your evaporator coil by gravity. So that is a natural occurring process of moving the refrigerant through the system where you don't need any compressors. So the CO2, as you're introducing heat, I think 1 degree C elevates the pressure of CO2 by 30 psi. So that moves up to the gas cooler, condenses into a liquid, and falls back down to your evaporator coil. So when you have colder temperatures where you can do this, your PUEs of just that system without reclaiming any heat are very low. I just wanted to show kind of the amount of economizers hours that you can get in different areas of the country. So it's related to the climate in whatever zone that you're installing this equipment, but we also allow you to do adiabatic gas coolers to help in warmer climates where we can maximize the free cooling hours that we get. These other lines, or the other color lines here, are the different modes of operation that you would have with a transcritical CO2 system. I wasn't planning on getting into the technical details, but basically you have transcritical cooling and then you have subcritical cooling. And subcritical cooling happens when you get below the critical point of CO2. That green line is where we have mechanical cooling, but we're actually modulating the compressors to save energy till we can get to the point where we can lock out the compressors and do free cooling with the system. So just a quick introduction of what our equipment looks like. It's fairly similar to what you would see in any perimeter style cooling system. These two units happen to be 15-ton upflow units connected to each gas cooler. Our 15-ton machine is a single circuit machine where we just have this on the right, our indoor unit hooked up to our gas coolers that are located on the roof. Just wanted to show you a picture to just kind of think about this. This isn't something that's extremely different than what you might be used to when you think about perimeter style cooling or air cooled technologies. One of the other applications that we have is row based cooling, and this is pretty unique because we have our gas cooler condensing unit, and then we have that hooked up to CO2 lines that go into your row based cooling unit. So this was, we were asked to design row-based cooling with CO2, and this was a design we came up with to basically allow for free cooling when we could, but also running CO2 lines directly out to the row-based cooling. One of the other, asks that we had was, well, if we do have a water loop in the building, and this one happened to be chilled water, but we didn't want to run chilled water to our racks. So we hooked up a heat exchanger, which is on the right, which is our CO2 to water heat exchanger, that will take the heat from the data center and reject it into the chilled water loop through CO2 lines going right down to that data center cooling equipment. I just wanted to show you this because I think it's important to where we want to go in the future, and basically figuring out how to move the heat from the data center into something useful. This is a nice solution for that with a CO2 to water type heat exchanger. Just some more photos, just kind of showing, upflow, downflow, our gas coolers, the one that I showed you before, but also our row-based equipment in pod format. Up here on the right, it's a nice photo because we get to show kind of the simplicity of the CO2 piping going into our row-based cooling modules. Where I was telling you about the capacity or the amount of heat that CO2 can hold, you require less gas, which actually makes the pipe smaller than what you would see in a normal synthetic refrigerant-based system. So this is an introduction of the data center cooling equipment that we have, but while we were developing that data center cooling equipment, our business was primarily in industrial refrigeration. And this is one of our first applications where there was a hockey rink up in Canada, so big ice rink. And next to that ice rink was the library and also some swimming pools. But the old ammonia screw or reciprocating compressors that we had that shown up on the top, they were approaching end of life. And so we stepped in with a CO2 based solution where we could make the ice in the hockey arena, but also in this application, we had 5 heat exchangers that were able to create different temperatures to be reused throughout this facility. So one, this isn't the chiller that I just showed you in the other picture, but these are our chillers for transcritical carbon dioxide refrigeration. And the first one where we actually did heat reuse, we were able to make domestic hot water. We had a heat exchanger for a snow melt system in this building. One of the requirements of a hockey arena was an enthalpy wheel to dehumidify the space. So we use one of those heat exchangers to regenerate that desiccant wheel for dehumidification. We also had a heat exchanger for pool water heat. And there was a few spaces in the building where we could do comfort cooling air preheat with the heat exchanger that we provided. So it was a pretty unique application where the chillers were selected to make the ice for the ice arena, but also we were able to, instead of rejecting that heat outside, use it in a useful way throughout that facility. I just wanted to just kind of show you examples of, industrial CO2 industrial refrigeration chillers. These two, I'm showing the heat exchanger sides of the chillers, but these heat exchangers can be selected for various temperatures and different applications based on a constant cooling load. So cooling's first, and then you're reusing that heat second when you can. So one of the things I think is unique is the CO2 to water heat exchanger. And I just, one of the things that we're looking at in terms of in the future, what we'd like to do and what some of our customers and partners have asked us to do is to create a perimeter style cooling unit, which can range anywhere right now between 15 and 48 tons worth of cooling. Those are our standard building blocks. We're always looking to do something bigger, but the idea is you have an indoor perimeter style unit, which is sending heat up to your gas cooler, or sending that hot gas up to your gas cooler. Like I said, we could do free cooling by bypassing the compressors and allowing the R744 CO2 condense back into a liquid and fall down to your evaporator. But with the heat exchanger, the picture I'm showing on the left, we can send that hot gas to a heat exchanger so that you could put it into a building loop. So when you need heat, we're running compressors to move the heat from the data center into the building. But if you don't need heat, we can lock out the compressors and go into a free cooling mode. So when temperatures allow outside, you don't have to run your compressors, but if you want to reuse the heat, you're running your compressors to move the gas into these heat exchangers. So that's kind of one of the exciting things that we're looking forward to in the future, a perimeter style unit with heat that could be rejected into the loop. The heat exchanger I'm showing on the right side is another CO2 to water heat exchanger. This is one that we typically hook up to our row-based units when you're hooking it up to a water loop. It's uninsulated, but I just wanted to show, you have our stainless steel piping connections coming out on the left-hand side, kind of right at you, but you also have your hot or your chilled water piping connections kind of in the middle. So this is 2 heat exchangers. So one of these heat exchangers could serve 2 row-based cooling units. The row-based cooling units are about 40 kW a piece, but we are looking to develop another row-based cooling unit that will do about 100 kW worth of cooling in a fairly small footprint in the data center. With CO2 able to hold more heat than the synthetic refrigerants, we need less heat exchanger area. So our heat exchangers can be smaller, whether it's your evaporator coil or your condenser, which makes our units a perfect application for a retrofit system. If you had something that's using synthetic refrigerants that you want to eliminate, I haven't seen a case where our units at the same capacity are anything but smaller in size. The footprint for a synthetic refrigerant system is bigger, ours is smaller. So it makes it easy to upgrade facilities with natural refrigerants that were historically using synthetic refrigerants. I saw a question come through about the heat and what temperatures that we can achieve with CO2.
Yeah,
and I mentioned earlier that 131 degrees Fahrenheit. I'm sorry?
There's a few questions about temperatures. So yeah, if you address that.
I saw them coming through. I haven't read them yet. But maybe this will answer some of them, and then I can go through the questions, and then and maybe we can answer a few of them if we have time. Because this is my last slide. But that 131 degrees Fahrenheit hot water is one of our sweet spots. So basically, I have a 200 kW chiller or 80-ton chiller that's making 30 kW or 300 kW worth of heat, excuse me. As you increase the temperature with a CO2 based system, the amount of heat capacity that you can get out of that machine or that system will decrease. So if you're going up to 140 degree water or 150 degree water and your chiller's 280 kW, you might not get, you're going to get less than 280 kW worth of heat as you start increasing those temperatures. So it's something, on the industrial refrigeration side of our business, those systems are always something that's almost very custom for every application, and every degree and every kW is designed for what that application is. In the data center business, we want to come out with general building blocks. Now, I'm not saying we won't entertain questions about custom chillers that can do heat recovery, but our goal is to have certain building blocks that can be applied in data centers and used how they want it. And that was where the 80-ton chiller that I started with in a data center application, I think it's perfect, creating 131 degree water. If you need a different temperature, we can take that offline and talk a little bit more about that. But that was the introduction of kind of what I wanted to talk to you about. We're excited. We are an ATMO approved manufacturer of refrigeration equipment. That was something we got a couple of months ago. So I'm going to go through some of these questions and see if I can answer them.
Yes. So let's open up the question. And people who posted the questions in the chat, if you want to ask yourself the question, you can unmute yourself and ask the question. So if you have some follow up, we can do that, or we can read the questions, whatever you prefer. So, Greg, if you wanna ask that question yourself, or we can read it. I guess we will read it. So, Seth.
Yeah, no, so I think, yeah, Cosmo, you kind of, the short answer is, yeah, as you elevate temperatures, you're going to get less capacity out of the heat, but the hot water side stays the same, but the chilled water side gets warmer. So yeah, I think the application that I showed was 44 to 56 degree water. Now, arguably, that's pretty cold. Like, you know, in a data center which requires nothing but sensible cooling, you know, it doesn't necessarily require latent cooling, you can elevate your chilled water temperature. If you design the system for higher chilled water temperatures, the efficiency and also the temperature of the hot water you can produce, it'll be better. So, you know, I think, you know, when we discuss this, we kind of come up with the approximation of what temperatures and capacities you're going to get, and then we'll do our selections to get that information to you.
Does that mean you're also running at a higher pressure then, when you're getting those higher temperature waters and higher temperature?
Sure.
Both on. Yeah.
It's you know, CO2 is a high pressure refrigerant. So I think you'll see the operating pressures of CO2 are about 4 times greater than what you would see with the synthetic refrigerant R410A. You know, so yes, these are CO2 to water heat exchangers that can withstand a significant amount of pressure. When just our standard equipment, you know, we design our gas coolers to operate around 105 degree Fahrenheit. But when we do that, we have our pressure relief valves set to go off at around 1740 PSI right now. So these pressures are pretty high compared to synthetic refrigerants. And part of our installation method addresses, or all of our installation method, addresses those concerns. You know, when the system is installed properly, you know, natural refrigerants need to be something that's considered now. You know, people are, you know, starting to take inventory of the amount of greenhouse gases that they own. This natural refrigerant CO2 will never be phased out, and it's something that can eliminate all of those concerns. So where CO2 is a good fit as a refrigerant, it needs to be considered, in my opinion. You know, one of the things I see is CO2 captured from the atmosphere. Well, as far as I know, when you are manufacturing R744, basically refrigerant grade CO2, it's done as a byproduct of manufacturing ethanol. It's, you know, there's different grades of CO2. There's CO2 that you could use in a brewery or for some food process application, but then there's R744 refrigerant. It's still about $1 a pound, if you know, in a nice round number, but R744 is manufactured so that it's very dry and doesn't have any moisture in that refrigerant. You know, another question: which HFO has a GWP of 700? You know, there's a chart out there that shows all of the available HFOs and what their global warming potential is, but I don't know that chart off the top of my head.
Seth.
Yes.
Seth. Yeah, you skipped my question actually.
Okay.
About, because you showed a very nice table with the GVP of different refrigerants, and I was missing water as a refrigerant. What is your opinion about water as refrigerant as an alternative?
So when I think of water as a refrigerant, I think of water as a refrigerant in absorption chillers, which I think absorption chillers are a great way to reuse heat into a data center, but you have single stage absorbers and two stage absorbers and a lithium bromide, or I don't know what other kind of solution you have to facilitate the phase change with water. But yeah, I've worked in applications that use absorption refrigeration before, and if that can be used, that's a great technology. So yeah, water as a refrigerant is great.
Compression chillers. I was meaning water as refrigerant for compression chillers. There are very few, I think, but there are some cases.
I would be very interested to learn more about that, because that's not something that I know too much about.
All right.
So Jim asked the question. I'm trying to.
Yeah. What are the refrigerant operating pressures in evaporation and economizer, and what is the lubricant, if any, in the system?
Yeah, let me see. Oh, yes. So I don't know. I just lost my screen. So maybe I'll come back here. Yes, in a CO2 based system, you need a POE oil to have lubrication throughout the system. Because the velocities of gas through the pipe are pretty high, and because of the properties of CO2, you don't need to trap our systems like you would trap a synthetic refrigerant-based split system. The pressures you might see somewhere around 400 or 500 on the low side and 1500 on PSI on the high side. So that is much higher. Let's see. So.
Yeah, Mark is asking about using gravity system, which I think you already answered. I mean, it's a thermosiphon without pumps if you do free cooling, right?
Exactly. I mean, that's exactly what this system is. The thermosiphon effect is what basically moves the refrigerant through the system.
If you don't want to recapture the heat, if you don't want to move the heat from one place to another, but you just do cooling, free cooling.
Yeah, free cooling is we call it the patent that we have is called the rain cycle, but the thermosiphon.
I saw that name in the presentation and I couldn't understand what it was. Okay.
No, it's just the gas migrates up to your gas cooler and then condenses into a liquid and falls back down. So you know the free cooling cycle and just CO2 in general, your heat rejection device needs to be higher than your the evaporator in your system. And that rain cycle is just kind of mimics what you would see with the rain cycle.
What's the highest temperatures can be achieved on the hot side? I mean, what temperature on a high grade heat can we achieve? Which is kind of already addressed that, but if you want, repeat that. You said about 130.
Well, I think we have on the industrial side of our business applications that can get up to 170 degrees Fahrenheit. But when you do that, you're using your compressors a little bit more than you would if your temperatures are lower. So there is a balance about the heat that you can make to do the cooling that you need. Yeah, we can get up to those types of temperatures if needed. But that, like I said, that 131 Fahrenheit was a sweet spot of ours.
There's a question for. Sorry, go ahead.
In that swimming pool application where we had the industrial refrigeration equipment for an ice skating rink where we were moving heat into the swimming pool. You know, when they designed that system, they had our heat exchanger for pool heat, but also pipe next to it was a boiler to add heat if our system couldn't give enough heat to keep the pool warm in the winter. But through the first few years of operation, they never even they didn't need to turn that boiler on. So the heat that we were able to give was sufficient to keep the pool warm, but there was the design in case to add more heat in a different way.
There's a question for Don Mitchell, I guess. Can we use Victaulic piping for CO2? We have Don here as part of Victaulic, so he can probably answer that.
I'll have to double check that. Sorry, I don't have that off the top of my head. I know that we've been testing against a lot of liquids and fluids, but haven't specifically checked that one. I owe a correct answer, so I'll get back to you.
It's a pretty high pressure refrigerant, and when we talk about the methods of installing our systems, we're looking at stainless steel tubing and stainless steel piping that's held together with orbital welding. You know, the issue is you have the burst pressure of CO2. You have to design your piping for the worst case, and the pressure that's the worst case is 5 times the pressure that you would see in the system. So what we're seeing, or what we recommend in our installation, is to do that with stainless tubing. Stainless tubing you can bend, and then it comes in 20-foot sections. So you bend it the way you need it to bend, and then we have an orbital welder, or we don't have the orbital welder, but there's welding machines that are orbital welders that you clamp on the pipes where they come together. And it has a rotating head on that forms that weld through the pipe. If there was something like a Victaulic connection that could make this process easier.
What's the max diameter you're working with as a refrigerant?
So usually in the systems, in the standard systems that we have, we'll see an inch to an inch and a half pipe diameter. In some of the industrial refrigeration applications, we might have a 2-inch or 2.5-inch pipe, but typically smaller than what you would see with a copper pipe installation.
I'll double check, but below 2 inches, the couplings are rarely because it's a groove coupling method, and there's other systems of connection, but to your point, it's a high pressure system. Above 2 inches, we might be able to do something there, and I'll check, but thanks.
That would be great.
Seth, I have a question related to that. So are the polypropylene pipes totally excluded for your system?
I'm sorry, I had a hard time hearing you.
Are the polypropylene pipes, so plastic pipes, are totally excluded?
Can you use plastic piping?
No.
Right.
No, I mean, we don't have
a use case.
Standard copper pipes can't handle the pressure. I mean, it's the stainless pipe that we recommend for installation of these systems, or tube.
Good.
So Seth, not to put words in your mouth, but would it be fair to say that this is a solution that is ideal for small to medium size data centers, not hyperscalers?
I think, right now, yes. I mean, we want to take this application and allow it to be used in data centers that are much larger. So megawatt, 2 megawatt data centers might be good for the building blocks that we have today. But, we'd like to say, if we can design for a much larger building, with CO2 as your refrigerant system, taking the heat from the data center outside, if we could use CO2 as a refrigerant instead of chilled water plants, you can eliminate a significant amount of the pumping energy that you would see in those type of facilities. So we're working on that, but this is being 10 years into it. We've developed these building blocks that we think are good to bring to market for anybody else who would like to consider and use these systems. But that new design for a data center is something that we're completely capable of doing. We have industrial refrigeration equipment that can give you up to 100 tons worth of cooling in an outdoor package. So it's the compressors, it's the gas cooler, all as one package. If we could figure out a way to hook that up to an evaporator, whether that evaporator was for chilled water or technical water loop or for air, that would be a fantastic solution that could save a ton of energy with all of the pumping that you would typically see in a traditional type chilled water loop system.
And let me ask you actually kind of a follow-up question. For instance, in your example of the pool heating and the office heating, how far can you actually move the heat with CO2? I mean, are we talking about 100 feet, or we're talking about quarter of a mile?
So with CO2, the horizontal length of piping to move heat from one space to another depends on the elevation difference between the gas cooler and where you need to go. So we have equipment that is installed with a gas cooler or condenser that's 13 stories above your evaporator. So that's your vertical height. But as that vertical height increases from about, let's say, 7 feet to maybe 20 feet, you can almost have an unlimited amount of horizontal piping. So I don't know if I would say, oh, we can go up to a quarter mile or a mile, but it is something that we would like to discuss further. I just don't know what the maximum is. But for in terms of a standard one of our installations, you can have 300-400 feet of horizontal piping, and that's easy for us.
Because the advantage, one of the advantages that I see is that CO2 piping is small in diameter.
Correct. I mean,
so you can move quite a relatively large amount of heat with a small pipe.
That's one of the advantages we're seeing in terms of the installation costs of our systems, is that copper's increased in price pretty significantly over the last few years, where stainless hasn't increased as much as copper. But also, so now when you're comparing a traditional synthetic refrigerant type system versus installing one of those versus installing a natural refrigerant CO2 system, your pipes are smaller in diameter. So the copper's gone up in price. You need larger diameter pipes than you would need if you were installing CO2. So it levels out the material and installation costs of installing a CO2 type system.
But Seth, actually in the real use cases, the interface with the heat off-taker is actually much closer to the chiller, right, than to the heat host. So in the real case, this is not happening, right?
It doesn't need to be, though.
It doesn't need to be. And the one picture I showed in the beginning, and I'll share this presentation so you guys can go back and look, that chiller sat in a mechanical room with just chillers. We then installed the heat exchanger that replaced that natural gas boiler right to where that natural gas boiler was sitting.
Okay.
Because otherwise you lose the advantage. Otherwise you lose the advantage of the small pipe, because if you bring the water to the heat exchanger, then you have to bring water. While if you bring CO2 to the boiler or the boiler replacement, you move CO2 with small piping.
Yeah.
So it's a more expensive piping, stainless steel piping. It's more expensive, it has to be insulated. It's more expensive, but it's much smaller. I mean, in some cases that is significant.
Correct. So yeah, you might want to put that heat exchanger where you had that source of heat, or where that source of heat is.
You use the heat. You put the heat exchanger where you use the heat.
Right. Correct.
Alex, I see that you have a question. I don't know if you are still connected. If you want to mute yourself.
Yeah, no problem. Yeah, so I was just asking the question that, fair enough, in regards to the hyperscale market, I kind of agree with you in the sense that we're probably a better way for this to be used as your primary cooling source. However, would it be something you'd be looking into in the future to basically almost reverse your cycle completely and look at it to be used in terms of your CO2 refrigeration systems almost as a top-up heat pump to then be used in tandem with existing hyperscale chilled water systems? So then we would then be taking off sort of higher return chilled water temperatures, taking that into your, let's say, reverse chiller, and using that to basically top up and then to hopefully redistribute back out into local district heating systems.
That would be a very interesting application. I think, yeah, I think it would be something that I'll leave my email with, and maybe we could talk offline. But I think, you know, it's we have our building blocks now that we want to make everyone aware about and that they're available. But those types of applications are something that requires some investment with engineering and the engineering of designing these systems. But we would certainly love to talk about it more.
Would you put your email in your presentation that you will share?
Yeah, I have it on the first slide and the last slide, and I'll email it to you so we could put it on the wiki page.
Perfect.
Cosimo, this is Suresh Pichai, Quinix, and I have a comment. We are aware of another company in Europe that actually uses some kind of a rollable high pressure tubing instead of stainless, and doesn't require welding similarly. And they have district systems installed in Switzerland, I believe. And their limit is around 1,000 meters for their system. So it's very similar. If somebody wants to know the name of the company, I can provide that, but I don't think it's confidential.
I think
I'd
they
like
want
to
to
know.
sell their pipe.
Yeah.
I would say.
Go ahead.
No, but yeah, thank you, Suresh. Thank you. Yeah. I mean, we are almost at the top of the hour. Seth, thank you very much for your presentation. It was very, very interesting, as expected, to be honest. And so the recording and the presentation of this call, like all the other previous calls, will be in the wiki page that we, Jaime and I shared the link a few times during in the chat box. And as said, Seth has his email in the presentation. So if you wanted to get in touch with him and ask one-on-one question, I guess Seth is more than available to sell more of his products.
Yeah. Well, thanks for listening, guys. This is exciting to be able to introduce this to you. So thank you.
Thank you very much. And I'll next week again is going to be advanced cooling facilities, and then in 2 weeks, actually next week it actually is Thanksgiving. I'm not sure we're gonna have a call, but in 2 weeks we're gonna have a call for sure for heat reuse again, and we will present our white paper, right, Jaime?
Yeah, exactly. We'll show you what we have done so far, and as I said, in the wiki link you have access to the guideline as well to comment. So the 101 will be also another topic of discussion next time. So thank you very much, guys. And see
Thank you very much, and have a good rest of the day.
Bye bye.
Bye bye.
Nice call. Thanks.